So hello everyone, my name is Renaud Lambiot and I'm here for this first video of C5.4, the course on networks from the Mathematical Institute. So in this video, in this first video, what I'm going to do is just to give you an overview of the content of this course. I'm going to try to give you some motivation on why networks are important as a model in many situations. And also try to give you an overview of all of the different types of problems that we're going to be considering in the next few weeks. But let's start with the motivation. So personally, as a researcher, I'm interested in complex systems. And what I mean to be a complex system, well, actually, there is no unique definition of what a complex system is. Here is one definition that I took from the Encyclopedia of Complexity, which basically says that complex systems consist of a large number of interacting components, and the interactions give rise to emergent hierarchical structures. The components of the systems and properties at systems level typically change with time. So here you have a number of keywords that are quite important. You have interactions, you have changing in time, you have large number. So here you need to think of all sorts of situations where you would have a large number of entities that are interacting with each other. And the combination of all of these interactions leads to some interesting behavior. So it could look a bit vague for the time being. So let's take a very concrete example. So, well, unfortunately, we are by video here, so we are not around in the street looking in the sky. But if you are walking around in the countryside and you are looking in the sky and looking at birds flocking together, this is a very good example of a complex system where you would have a large number of birds, each of them interacting with their direct neighbors, adapting their direction depending on the direction of their neighbors in the flock. And through the combination of all of these local interactions, you have the emergence of these beautiful patterns that are at the same time geometric. You have nice geometrical features in the sky, but also dynamical, because these geometrical features are evolving in time. And well, this is just one example where the combination of local interaction lead to interesting emerging phenomena. But there are many other situations where this happens, and a very good example might be in social systems, elections. In elections, you have people debating with each other, discussing with each other, and the combination of all of these interactions lead to the formation of collective opinions, and in this case, to the election of one person to be, for instance, the President of the United States. Now, when you're confronted to complex systems, there are a certain number of tools that can be used. So, for instance, people use agent-based models. People are also using dynamical systems, and especially chaos theory and nonlinear dynamics. People are also using stochastic processes because, and this is something that we're going to be discussing in detail, noise and randomness is a key element of many systems. Also, well, even more nowadays, people are using tools from data mining and optimization, which again is motivated by the fact that more and more often now the models tend to be motivated by real-life data sets. And then there are networks, which is the topic of this course. Now, okay, so actually networks are an extremely powerful language and framework to describe systems because of their generality. And indeed, many systems that can be very different in nature can be represented by exactly the same language and the same tools. And here you have two examples. On the left side, you have an example of a social network. On the right-hand side, you have an example of a biological network. Both are extremely different. The nodes represent different entities. The interactions represent different entities. But yet, you can use the same language and the same tools to represent and analyze these systems. And even within social networks, you may have extremely different types of networks. You can think of collaboration networks, the way scientists collaborate with each other. You can think of communication networks, the way each of us communicates by email or mobile phone. You can think of online social networks, Facebook, Twitter, and same for biological networks. In this example, it was an example of a protein-protein interaction network where the nodes are proteins and the links represent interactions between them. You can think of neural networks where you would have, that's a good example, the brain. Or you could also think of food webs where you would have species interacting with each other, for instance, eating each other and forming complex food webs. Now, as I said, networks are very general, but it's something that needs to be understood is that networks are just an abstraction of reality. And indeed, this is an example from the famous famous work of Euler on the Königsberg bridges, where in this case, Euler was interested in the notion of connectivity on a map, and where we would have different regions of the city and bridges that connect these regions. And clearly, you could have a very detailed representation of this on the left, where you would have a proper map. But actually, there are many details and many aspects of this map that are completely irrelevant if you're just interested in connectivity. And for instance, you could remove the buildings, the way the buildings are set up, but also you can remove the exact location, the way physically, geographically, the regions are set up on the map. And if you do so, you go from something that is more detailed to something that is more abstract, and you have at the end this network representation that really focuses on the key ingredient for connectivity, and that would be the presence of nodes and links that are basically connecting these nodes. And this very same tool of this very same exercise of abstraction can be done in very different situations, as I said. On the top left, you would have a representation of the internet with nodes being routers and links being physical connections between them. On the top right, you have a very famous example. Actually, it's an example that made the cover of the New York Times in the 1930s. That's an example where you would have that nodes represent kids in a primary school, and the links represent the fact that they play with each other. And as can be seen here from the symbols, so the symbols represent the gender of the kids. And you can see that clearly there's a clear divide, and the fact that the boys play with the boys and the girls play with the girls. On the bottom left, you have a functional network of the brain, and at the bottom right, you have a food web where, as I said, species are interacting with each other, typically in a very hierarchical way. Now, once you have a network, there are many different types of questions that you can that you can ask. And one of the fundamental questions of network science is to understand the relation between the structure of a system and its dynamics, its linear dynamics. And typically, especially if you have a linear dynamical system, the kind of problem that you have looks initially very simple. You have this system of linear equations where x would be a vector, where each component describes a variable that is defined on each node. And then you have a coupling matrix L, and this coupling matrix encodes basically the interaction between neighbors on the graph. So it encodes the topology and the impact of the topology and the dynamics. And as a result of this, you have the system of n equations with a big coupling matrix L that basically tells you how the nodes are interacting with each other. And this is something that you've seen in the first year, how to solve these systems. It's not difficult in principle. But what is more interesting is really to understand how the structure of the graph translates into the properties of this coupling matrix, and in particular in its spectral properties. Now, when you have a problem like that, you can look at it from two different angles. On the one hand, you can try to understand what is the impact of the structure on how the spreading dynamics takes place. So you can think of random walks, which we're going to be considering in detail, consensus dynamics, and ask, or embedding spreading, and ask how does the topology affect, speeds up, slows down, the way the dynamics takes place. Then there's another angle that is something that we're going to be covering as well is, is it possible to use dynamical systems to explore the graph and to extract some interesting features, interesting properties that the graph has? And these two angles are two aspects that we're going to be considering during this course. Now, something that is also quite important to keep in mind is that, real world networks, they tend to present a balance between order and randomness. Clearly, if you think of your social network, it's not completely random. There are some social forces that shape the way your social network is organized as it is. But at the same time, on top of these social forces, you also have randomness. People you meet randomly in the bus, with whom for some reason you start to talk and you start to befriend each other. So it means that you have this combination of forces that organize your social network and randomness through random connections, random meetings that may lead to links in your social network. And this combination of order and randomness, actually, it's a question that was at the core of what is very often seen as the seminal paper in network science. It's a paper from Watts and Strogatz of 1998, where actually they were trying to understand what is the impact of the order and randomness in topologies on dynamics. And the way they did was to propose a very simple, crude toy model of the way social network or networks would be organized, where what you can see is that on the left, you would have something that is completely regular. It's basically a one-dimensional lattice. On the right, you have something that is completely random. All of the links are organized completely randomly. But then they have a parameter that allows them to interpolate between these two extremes and to define what they call small world networks that would have a balance between local order and randomness. And these randomness creating shortcuts in the system. And as you'll see, this combination is extremely important to shape the way dynamics takes place in systems. Okay, so this course is going to be following quite closely my lecture notes. So you have lecture notes that are available for you, where I try basically to be as complete as possible. And actually, some of the part of the lecture notes will not be covered here. There's a bit more, and this is for your own interest if you want to read about it. Now, basically, for each week, we're going to be looking at specific sections. So here today, I'm going to be talking about motivation, which I do now. And then what I'm going to do is I'm going to just be doing some refreshers on some mathematical concepts that are important for this course. And as I said, because of the importance of randomness, we'll have to use stochastic models. And so I'm going to be doing just a bit of refreshing on Poisson processes, random walks. I will talk about power law distributions. I will not have the time to cover everything, but there is also like a small reminder on matrix algebra, Markov chains, and so on. So you're very welcome to have a look at those, and they are just written so that you can use them as a reference point if you have any kind of trouble afterwards in the course. Now, next week, then, we're going to be starting to look at networks. And actually, we're going to first have a very short introduction on graph theory, only the concept that we need. And then we're going to be looking at simple basic methods that help you to characterize the structure of networks, and in particular, the centrality of nodes. And we will also talk about spectral properties of graphs and networks. The week after, we're going to be talking about random models for networks. Because indeed, very often when you have an empirical network, you have a graph, the one that you measure in real life, and you want to construct a randomized version of it in order to test some hypotheses about the graph structure. There are all sorts of models that can be built that make certain assumptions about the underlying topology, and we're going to be looking at some of these models that allow some analytical calculations. Then the week after, we're going to be looking at a very key problem that people look at usually when they look at networks, which is the problem of community detection. So what is community detection? It's basically a clustering problem. You have a graph and you try to cluster the nodes together by looking for dense groups of nodes that are very cohesively connected with each other. And basically what you try to do is to have a graph and to extract these groups in an algorithmic way. And we're going to be looking at some of these algorithms. Then for week 5, we'll start to look at dynamics, and we'll try to understand the impact that these communities, these clusters have on dynamics. And we see that the presence of clusters, of communities, tends to affect dynamics very much because they induce the presence of bottlenecks for the dynamics that slow down extremely much the way information can flow from one part of the graph to another part of the graph. Then we'll look more specifically at one type of dynamic that would be the one of random walks. We define random walks on networks. And then we'll go to this second aspect of the question of, after understand how the structure affects the dynamics, we'll focus exclusively on how can we use dynamics, and here's random walks, in order to reveal something interesting from the underlying dynamics. And then we're going to be finishing with a topic that is, well, something that is very topical nowadays, trying to see how can we incorporate network knowledge, network information in the way to do epidemic modeling, and how can we enrich epidemic models that are usually done in a mean field fashion by incorporating networks about the way the people are interacting or about the way different regions of the world are basically connected by means of mobility patterns. Well, that's a lot. So what are the key objectives of this course? So the key objectives would be, well, first of all, we want to try to propose ways to quantify the structural properties of nodes in a graph and to estimate which ones are important. Well, if you want to quantify the structure of the network itself, or can we have measures that tell you something about a graph? What are their important properties? We'll then build some random models that are critical in order to test the importance of certain factors in the way a network is organized. We'll look at the problem of community detection, finding groups of nodes that are densely connected. And finally, we'll try to identify certain structural properties that are associated to an impact on the dynamics. And in particular, well, for the spreading of information and of virus, for instance, on the graph. So those would be the kind of questions that we'll have in mind in the next 8 weeks. So, well, as you know, well, there are some problem sheets associated to this course, and all of them try to find the right combination between numerics and analytics. This is just an example where you see that, for instance, question 3 is more, well, about analytics, about the math, where you have to show some understanding about some graph theoretical concepts. But then you can also have, for instance, question 5, that would be some more numerical question where you are asked to write a code to generate some graphs according to certain rules. And so the whole course is going to be basically some sort of combination of these two aspects. Now for the numerics, well, you can use any language of your choice. I encourage you to use, well, Python, because I know that most of you like Python, first of all, but also because many libraries exist in Python that facilitate any kind of modeling and manipulation of networks. And so, for instance, NetworkX is a very good example of that. But you're very free to use any language that you choose. Now, another point that is quite important, I suppose, is that when you're always very curious usually about the examination. Well, for the examination, it's going to be done with a mini project, as has been done in the last few years. This is an example from 2018-19, so 2 years ago, where the mini project is typically, well, what needs to be handed in is a project in the form of a research paper. And you are basically asked to explore the literature in a very specific problem. Well, it still allows you to have some flexibility. So here I asked the students to look at the concept of non-backtracking random walks, something that we had not seen in the course, but was a natural extension of what we had seen in the class. So basically, I always try to find a topic that naturally extends on what we've seen and allows the students to explore the literature and to find a question within this umbrella of non-backtracking random walk that year that basically that they find interesting. So this is a creative work, a small research project, and each year we have a different topic. 2 years ago it was non-backtracking random walks. Well, this year obviously I cannot tell you what it's going to be. Now, okay, so, well, this is the end of this first video that was about the motivation of the course. So, well, now what we're going to do is we're going to be looking at some, just a bit of math, about some mathematical concepts that are particularly relevant. And basically what I'm going to be doing is to focus on the parts B, C, and D. So we'll have some new videos coming in a second where you're going to be looking at the basics of renewal processes, including Poisson processes, also random walks and diffusion, and then we're going to be talking about Pobollo distributions, because as we'll see, they tend to play a very important role in graphs and networks. So thank you for listening to this first video, and yeah, you're welcome to look at the next one. So welcome everyone for this second video of the first week of the course of networks. So as you discovered in the first video, randomness and stochastic processes are key elements if you want to model networks. And that's because most empirical networks tend to have a combination of order and randomness. And in this video and the next video as well, we'll be looking at very simple stochastic processes in order to introduce this very important notion of master equation. So in this video, we'll be looking at Poisson processes that are a typical example of a renewal process. So what is a Poisson process? So typically Poisson processes are used as a very simple first order model to represent systems where you would have a sequence, a random sequence of events that take place in time. So here what you would have is that would be here the time axis. And you would have what appears to be a random appearance of events in the course of time. So you can think of, for instance, emails arriving in your mailbox, or the times at which atoms would be colliding in a gas. Well, these would be situations where clearly it doesn't seem to be predictable. There seems to be some randomness in the way these events take place. Now, a Poisson process is based on two extremely important assumptions. The first assumption is that the rate at which the events take place is constant. So you have a constant rate at each time, basically the rate of events is the same. And you also have a second very important assumption, which is the fact that the events are independent of each other. Yeah. Now, as we'll see, using these two assumptions, we'll be able to derive very important mathematical properties of Poisson processes. But of course, well, when you think about it, these are very strong assumptions, and it's very unlikely that they're going to be verified in many situations. So let's take emails, for instance. Well, clearly the rate at which I receive emails is not constant. I tend to receive more email during the day and many less email during the night. And so clearly there should be some sort of modulation in the way the rate of receiving emails is defined. For emails as well, can we assume that receiving emails are independent processes? Well, again, that's very unlikely, because very often emails are part of conversations, of threads. And well, if I receive an email, I reply, I receive another one. This is going to be leading to a cascade of emails, and all of those will not be independent from each other by definition. So clearly for emails, well, that doesn't seem to be a very good model, but the most important is that this is a model that can be used as a baseline and that you can then generalize in order to make it more realistic. And as we'll see when we'll be looking at the modeling of networks, we'll be proceeding in the same way. We will also build a very simple stochastic model of networks based on simple yet unrealistic assumptions. And then we'll be building more and more complex models that would be much closer to the truth, or to the reality. So what can we say about Poisson processes? Well, typically, let's first define a Poisson process. Poisson process. Well, the way it's defined is the following. So we assume that we're going to be taking a certain time window of length delta t, and we'll say that there's a certain probability q that an event takes place inside that probability q that an event takes place inside that time window. And clearly, well, this is going to be defining a rate, lambda, which is q divided by delta t. Yeah? And this is the rate at which event takes place given this probability and this time window. Now, as is often the case, we're going to be taking the limit when delta t goes to 0. And in order to make the rate non-trivial, we'll take at the same time the limit when q goes to 0, so that lambda is non-zero. Yep. And non-infinite. And we'll take these two limits, and it's going to be defining a rate at which events are going to be taking place in very small time windows. Now, clearly, because we take the q going to 0 and the delta t going to 0, well, in a very, very small delta t, we will either have 1 or 0 events that are possible. Yeah, because the Q goes to 0, it's impossible in a very small time window to have more than one event taking place just in one tiny time window, which is something that we're going to be using in just a moment. Now, when you look at Poisson processes, there are many things that you can derive, but one of the most important properties is P of nt, which is the probability of observing n events in a certain time window 0t. Now, well, by definition, what do we know? Well, by definition, we already know some of these values, because what we know is that the Q is equal to P of 1 delta t. Yes, Q is the property of having one event in a very tiny window delta t, when delta t is small, which is equal then to lambda delta t, when delta t is small. And we also know that 1 minus Q is equal to P of 0 delta t, so it's the probability of having 0 events in a very small time window of length delta t, which is equal to 1 minus lambda delta t. Yeah? And so here we exploited the fact that in a very small time window, you can either have 0 or 1 event that takes place. Now, using this, well, actually, we're going to be able to construct an equation that is going to be relating the P of nt with its expression for smaller values of t. And this is the essence of what is a master equation. A master equation tells you how probabilities evolve in time. And even if you have a stochastic process, well, you're going to be having equations that tell you how the probabilities are evolving in time. And so here what we have, and so I'm going to first write it down for you. So we have that the probability of having n events in a time window of t plus delta t. So it's going to be equal to a combination of two things. So let me first write it down. Okay. So it's a combination. So here basically you look at all the possibilities that will lead your stochastic process to have an observation of n events in a time window of t plus delta t. And when you think about it, you have two ways. One way would be to have n events in a time window of length t, and then 0 event afterwards. Yeah, and that would be what we have here. And n initially and then 0 afterwards. And another possibility would be to have n minus 1 in the first time window and 1 event in the next one. And these are the two only possibilities to relate the P of nt to the P of n t plus delta t. So here, actually, well, I've been making implicitly, I've been exploiting actually one of the assumptions of the Poisson process, because as we said, the Poisson process relies on this notion of independence. And here, indeed, I've been factorizing the probability of having n events in time t and 0 events in delta t. I've been factorizing that as the product of the two probabilities. That's why you have a product here and you have a product there. And so clearly here, well, by using this independence, I can write down an equation that allows me to relate the P of n t plus delta t to the probabilities taking place at the previous time. Now, what we're going to do now is we're going to be taking the limit when delta t goes to 0. And this is going to lead us to a differential equation, a system of differential equations. That would be the following one. Lambda P of n minus 1 t minus lambda of P n t, which is an equation that would be satisfied for n that is larger or equal to 1. And so we have a system of equations for all of the values of n larger than 1. And we also have another one here for 0, which is simply equal to minus lambda P of 0 t. And so it means here that we have a system of differential equations to solve in order to estimate what would be this P of nt. But this is not so difficult to solve because we can solve the one for 0 And then we have what's needed for solving the one for 1, and then for 2, and so on. So we can resolve this recursively to get the general expression for the P of nt. So, well, when you look at the first one for P of 0, well, what you have is P of 0t. It's going to be equal to a certain constant times exponential of minus lambda t. Now we need to estimate what is the c, what is this constant of integration. But what we know is that what is the property of having 0 event in a time window 0? Well, it's going to be equal to 1. Yeah. In a time window 0, the probability of having 0 events is equal to 1. So it means that from this we have the constant is equal to 1, and we have that the P of 0t is equal to exponential of minus lambda t. So this is the first property of the Poisson process that we just derived from this master equation. Now, actually, before we go and solve the P of nt for general values of n, well, actually, let's focus for a second on this P0 of t, because we can derive something else that is very interesting from it. So when you think about it, so when you have, if this is a length t, and this is here a certain length delta t, yeah, and you ask the question, what would be the P of 0t minus the P of 0t plus delta t? And these two quantities will be different, yes. So the probability of having 0 event in a time window t minus the probability of having 0 event in a time window t plus delta t. Well, this difference is actually the probability that for the first time you had an event taking place within the small time window delta t. So it means that this quantity here is going to be equal to a certain P of, no, let's write it down differently, sorry. Let's call it psi of t delta t. So basically it tells us the probability that for the first time you have an event taking place after time t. And well, if again you take the limit when delta t goes to 0, what you get is that this psi, and let's write it down with tau. Tau would be the first time when an event happens. It's going to be equal to minus dp of 0 tau divided by d tau, which is equal, from what we obtained earlier here, is going to be equal to lambda exponential of minus lambda tau. And so what this tells us is something else now. What we just got is that the probability of waiting a certain time tau before an event happens is distributed in an exponential way for Poisson processes. Now, the thing is that, so clearly because of the fact that all of the events are independent of each other, we will basically have that we'll have a certain time tau 1, for instance, after the first event, before the first event, and then a certain tau 2, and so on, and then tau n, and so on. And because we have that the events are independent of each other, each realization of this random variable will be independent of the previous ones. And this is something that is usually called the renewal property. Renewal property. So the inter-event times are independent of each other, and the Poisson process presents the renewal property. Actually, the Poisson process also presents another very strong property, and it's the fact that the P of tau larger than T1 plus T2, given that tau is larger than T2, it's equal to the probability of tau larger than T1. So what does it mean? It means that so if I have someone waiting for a bus, for instance, and the bus are arriving in a Poisson fashion way, and you ask how much time does he have to wait? What is the probability that the bus arrives after a certain time T1? Yeah. Well, it's going to be the same as a person who would have been for a certain time T2, yes, and no bus arrived, he's still there. And you ask, how much time should the person wait for the bus to arrive? Well, actually, the probability to arrive after a certain time T1 after the T2 will be the same for this person and for that person. Yep. So basically it means that, well, because, and this is because of the inherent nature of the Poisson process of independence and the constant rate. Well, when you wait, when you're at a certain point in time, well, all of the past is irrelevant. And hence the property of waiting for a certain time will be exactly the same initially than it is after a certain time that you've been waiting. Now, so what about now the general solution of the Poisson process? So as we discussed, so we obtained an expression for the P of 0t, and then you can solve recursively and get an expression for any value. And what you get is, well, what we're going to be having is that the distribution of the number of events in a certain time window of length t is going to be equal to lambda t to the power n divided by n factorial exponential of minus lambda t, which basically tells us that the property of waiting for of observing n events in a time window t is going to be given by a Poisson distribution. Yeah, and this Poisson distribution has a mean and a variance that are equal to lambda t. Yeah. Now, this is beautiful because, well, it means that from the Poisson process, very easily we can obtain key quantities that describe the stochastic properties of that process. But obviously, as we said, this is a very simplistic model, and so what you would like to do then is to use it as a ground on which to build more complicated models. And well, actually, there are ways to do so. And for instance, one way to generalize the Poisson process is to characterize inhomogeneous Poisson processes, where you have the possibility now to have a rate that is not constant anymore, but a rate that was going to be modulated in time. And for these inhomogeneous Poisson processes, and that's shortly described in the lecture notes, well, actually, you can also derive certain properties of it. It's a bit less easy, but you can do that. Another thing that can be done is, well, to try to get rid of this independence between successive events. And one way to do is to introduce, well, you want to introduce certain correlations between events taking place in time. Well, one way to do is to go to more general renewal processes, where you have that the inter-event time distribution will not be an exponential, but a certain distribution that might be fitted from empirical data, or to even go to more complicated models like self-exciting models, where events trigger the realizations of future events. But this is certainly something that goes beyond what we need for this course. I have some references in the lecture notes. You're very welcome to read them. And yeah, so this small video concludes our short introduction of the Poisson process. And in the next one, we'll be looking at random walks. So, well, hello again. So this is the third video of this first week of the course of networks. And what we'll do now is to look at the concept of random walks, which is a very simple model and very generic model for diffusion. So as we'll see, random walks play a very important role in network science. We'll be using random walks on networks very often in order to model the diffusion, for instance, of IDs or information in networks. But we'll also be using random walks as a way to explore a graph and to extract some information from that graph. But random walks have not been defined initially on graphs and networks. They have a much longer history. And they tend to have a very important place in almost any field of science where you have a motion that has some random, that has a certain random nature. And this happens in biology, in physics, in finance. So in many, many domains of science, you will see random walks appearing. So if you remember, in the previous video, we looked at the Poisson process, and the Poisson process is the simplest model for the way random events take place in time. Here we'll be looking at random walks, which is arguably the simplest model to generate random trajectories in space. So we'll try to model some random motion in space. And for the sake of simplicity, we'll be looking mostly at one-dimensional space, so the one-dimensional line. So just before we start, I just wanted to point to this very nice website. There's a website called Complexity Explorables, where you can explore a whole range of models that people use to model complex systems. And this is very nice because you also have some mathematical explanation of the behavior of the model, but also you can play with the parameters and observe how the dynamics takes place and evolve. And one of those small examples that is on this website is precisely about random walks. And here is an example where you have different random walks where you would have slightly different rules for the way the random walker is behaving in 2 dimensions here. And what's quite important to understand is that actually these tiny details in which the random walker moves are basically washed away after a certain amount of time. And what's going to happen, as we'll see analytically in a few minutes, is that, well, in a random walk process, you have a sequence of random jumps. And this sequence can be understood as a sum of random variables. And you know from statistics that when you have a sum of independent variables, well, asymptotically, by the central limit theorem, is going to be converging to a nice Gaussian distribution, independently of the details of all of the variables. And actually, this is also something that's going to happen here, independently on the details of the way the random walker is moving. If you look at things after a sufficiently long amount of time, you will see a nice bell-shaped Gaussian distribution emerge as the probability for a walker to be at a certain place at a certain time. So please go on this website. It's very nice to play with and to explore visually, at least, the properties of these random walk processes. But here, so we will not be looking at 2 dimensions just for the sake of simplicity, but we'll be looking at a 1-dimensional system. So what we have here is 1 dimension, which is our position. And what we'll be considering is, well, actually a certain situation where you would have a certain random walker. Initially, for instance, it would be located at 0. And then it is going to be moving at discrete times. It's going to be a discrete time process. And at discrete times, it's going to make jumps. And these jumps are random variables. So it's going to be making a jump to a certain R. And basically what we have is that we define a certain probability density f of r of doing a jump to r from 0 in 1 step. So clearly it means that if I had a walker that started at x, is going to jump to the location x plus r plus delta r. So it's going to move to this interval in 1 jump with a probability that is given by the f of r times delta r. Okay. Now, well, this f of r is actually just a parameter of the model. So this is something that we need to impose. It's the rule by which a walker makes a jump and where it goes in 1 single jump. Now, as we'll see, we will not need much information of this f of r to understand the behavior of the walker for long times. And actually, what will be, there are just 2 important parameters that we'll need is the v, which is the average of r. And so, for instance, if the walker is unbiased and goes as much to the left as to the right, this quantity would be equal to 0. Otherwise, as we see, it's going to lead to a drift in one direction or the other. And you also have a certain d that measures the variance of this f of r, defined as this quantity here. And as we see, these 2 quantities are going to be sufficient to describe the asymptotic dynamics of the walker for long times. So just of course, because f is a probability density, we need to verify that the integration from -infinity to infinity of f of r dr is equal to 1. Yeah. Now, okay, so how can we describe the motion of the walker? What we need to do is to try to write equations that the probability to be at a certain place x at time t is going to be satisfying. So what can we say about the time evolution of the probability to be at a certain time x at time t? Well, clearly what we need is an equation that shows the evolution of this quantity by jumps. Yeah? And we'll need to complement this equation by a certain knowledge of the initial condition. So for instance, we need to think that probabilistically, for instance, the probability that the worker was on 0 initially is equal to 1. Yeah? And then we'll have an ensemble of workers behaving randomly, leading to a distribution that's going to be evolving in time. So this P of x at time t, which is then, as we said, like the probability of visiting x, so probability of visiting x at time t. Well, it's going to be satisfying this equation here. So it's going to be the integration from -infinity to infinity of f of x minus x prime. And then we have the P of x prime t minus 1 dx prime. So where does this come from? Actually, it looks very much like the one that we got for the Poisson process. What we say here is that if you want to know what is the probability that you are on a certain x at time t, well, you have to look at the positions of the worker at the previous time at t minus 1. And so, for instance, it was on a certain x prime, and you say, okay, it's going to be the probability that I was on a certain x prime times the probability that I jump exactly towards x in one single step. So actually, this is the probability that I was on x prime and that I make the jump that I need to arrive on x. And as before, we can factorize these probabilities because we will be assuming that the probability to do a certain jump is independent on where you are at a certain time. And what we do here is that we have this quantity for one specific value of x prime, and then we need to integrate over all possibilities in order to look at all of the possible trajectories that would start from a certain x prime and arrive on a certain x. Yeah. Now, this equation is a convolution, and when you need to deal with convolutions, it's very practical to go into the Fourier domain. So just remind you rapidly what is the Fourier transform. So we'll say that P of kt is equal to the integration of -infinity to infinity of P of x t exponential of -i kx dx. So P of kt is the Fourier transform and with a small hat of this probability, where the k would be understood as frequencies, where x would be understood as positions. And from this Fourier transform, you can recover the P of x by the inverse Fourier transform, and the P of xt is going to be equal to 1 over 2 pi times the integration from -infinity to infinity of the P hat of kt times exponential of I kx dk. Now, well, when you need to think about the Fourier transform, what do you do? Well, actually, what you do is you decompose your P of xt in a basis of functions, and this basis would be this exponential of I kx. Instead of having a sum, you have an integration. So basically, you decompose your P of xt in a basis of exponential of I kx, where these here would be actually the coefficients in this decomposition. Yeah? And these coefficients can be obtained by doing some sort of like a dot product of your vector, yes, with the vectors of your basis. Yeah? This is very much like what you do in linear algebra. Now, something that is important to know is that the P hat of kt, the Fourier transform of P of xt, which by definition is the average of exponential of -i kx, well, actually it provides information about the moments of the distribution by looking at its behavior for small values of k. So we have that if you do a Taylor expansion for small values of k, we have 1 minus I k average of x plus 1 over 2 k square average of x square plus and so on, higher order terms. So all of the information about the moments is basically captured by the analytical behavior of P of kt for small values of k. Now, why did we do a Fourier transform? Because, well, as you know, when you have a convolution and you take a Fourier transform of that, it's going to be translating into products. And so it means now that the equation we're going to be having now is that p hat of kt is going to be equal to the f hat of k times the p hat of k t minus 1. Yeah. And here what we can do now is to iterate. And if we assume that initially we had that the p of x0 is equal to delta x, so initially all of the probability is concentrated on x equal to 0. All of the walkers are at the origin. Well, then we will have that the p hat of k0, our initial condition, will be equal to 1. And now, starting from this equation here, we iterate. Yeah. And what you obtain is that the p hat of kt is going to be equal to this f hat of k, the Fourier transform of this quantity here, right? The behavior in one single jump to the power t. And now what's happening is that, so if we want to find back what is the p of x t, we only need to do an inverse Fourier transform of this quantity, and we get 1 over 2 pi of the integration from minus infinity to infinity of f hat of k to the power t exponential of I kx dx. So it means that formally we found a solution of the property of being a certain x at time t by doing this Fourier transform and inverse Fourier transform, and we see that, well, we basically have just products that take place of this f hat of k that determines the properties of jumps, of single jumps. Now, what's very important, and well, I will not have the time to go into the technical details of how to do it here, but what's quite important is that actually when t is sufficiently large, what's going to happen is that many of the details of this expression are going to be disappearing. And actually, the dominating terms are going to lead us to the emergence of a nice behaved Gaussian distribution. So what we'll have is that when the time is sufficiently large, we'll have that this goes to 1 over 2 pi dt 1/2 times exponential of minus x minus vt squared divided by 4 dt, where the v was this quantity telling us about the symmetry of the walker, while the d here would be telling us about its variance, basically. And what we have here is that for long times we have the emergence of this Gaussian, where we have a drift term that tells us that if there was a drift in single jumps, we'll have that this Gaussian is going to be moving to the left or to the right, depending on the value of v. But at the same time, we also have that the variance of the Gaussian is widening, and this is diffusion. And so we have this nice Gaussian that is going to be drifting one way or the other, and at the same time becoming flatter and flatter. And well, actually, the technical derivation from here to there looks very much like what you do when you try to show the central limit theorem. Because when you think about it, a random walk process is just a sum of random variables, where each random variable is what's happening in one jump. So this was a very short introduction to random walks, and as we'll see, we'll be using random walks very much in the rest of this course. We'll do them on graphs in a discrete space instead of doing it in one-dimensional lines as we've done here. But you'll see that actually certain of these aspects that we've been discussing today are going to be coming back. So for instance, instead of doing Fourier transforms, we'll also do some sort of like a spectral decomposition that's going to be looking like it very much. But this is going to be for later. And well, thank you very much for your attention, and yeah, I invite you to look at the next video. So hello everyone, this is the last video for this first week, where we're going to be talking about power law distributions. So in the last two videos, we've seen the emergence of two very important families of distributions. We've seen that for Poisson processes, we have naturally the emergence of exponential distributions, while for random walks, through the central limit theorem, we have the emergence of these very nice Gaussian distributions. Now, the thing is that very often in real life, when you are confronted to real life data, well, you may be confronted to distributions that would be very, very different in nature from those two distributions. And this is very specifically the case of power law distributions, which, as we'll see, play a very important role in networks as well. So what are power law distributions? So here, this is a very classical example where we have been considering like a population of 10,000 cities, and we've been constructing an histogram that tells us about the frequency of cities having a certain size. And what you can see is that, well, this histogram is given by this shape here, right? That when you plot it in a log scale, so this is log here, this is log there, yes, takes the form of something that looks very much like a straight line. Yeah. So as we'll see, well, when you have such a straight line in a log scale, this is basically the sign that you may be confronted with a distribution that is power law distributed. Now, power law distributions have been observed for decades, for at least a century. There's like very important figures would be Pareto and Zipf, for instance. And it's been observed in a variety of contexts, like distribution of the size of cities, also like the different, the distribution of the frequency of words in text, for instance, where the would be appearing very, very often, while my last name, Lambiot, might maybe appear once and be among all of these words that appear very, very infrequently. But even within networks, power law distributions have been observed very often. And so here are 6 examples of degree distributions. What is a degree distribution? So when you have a graph, you have elements that are connected to each other. Yeah. And a very simple measure of the importance of a node is the degree. And the degree counts how many edges are connected to a node. So for instance, this node here has the degree 3, this one 1, this one 1, this one 1. So for this specific graph, if I was to plot the degree distribution, I would have, so this is 1, 2, 3, this is my k, and then I have 1, 2, 3, 4. I have 4 nodes, and I would have that 3/4 of my node have a degree 1, and 1/4 of my node has a degree 3. So that would be my degree distribution. Of course, in such a small example, it's difficult to characterize the shape associated to the distribution. But when you're confronted to networks made of thousands or millions of nodes, then you can properly calculate an histogram and try to understand, to model the distribution that is associated to that histogram. And so here you have 6 examples where here what you have is a distribution of a collaboration network where you would have mathematicians connected with each other when they write together. Here you would have a citation network where now the nodes are articles and the links represent citations from one paper to another one. Here you would have, here you would basically be having the World Wide Web. So the nodes are now this time, the nodes are pages and the links correspond to hyperlinks in this graph. Here you would have the internet where the nodes are routers and you have physical connections between the routers. Here you have power grids. Well, I think it speaks for itself. And here you would have protein interactions where you would have proteins and links represent interaction between these proteins. And what you can see is that in each of these situations, when you plot this degree distribution in a log way, you have something that, well, sometimes vaguely, sometimes more precisely, looks like a power law. So for instance, here, clearly, this is very much like a straight line, while this one, well, clearly this would be much more debatable. But still, you have some distributions that tend to be very, very broad and to have what is usually said to have a fat tail. But I'm going to be explaining to you in a moment what I mean by that. So let's define what is a power law distribution, and let's do it in a continuous way. For the discrete way, it would be very much the same. So we have a certain distribution that is given by this. X, it needs to be larger than a certain minimal value. So typically, degree distributions with a power law are defined only for positive values, but strictly positive values, because otherwise this distribution here would be diverging for x going to 0. And what you have here is typically a minimum value, x min, after which you have this power law decrease. Now, well, the C is there just for the normalization, and so the C is equal to alpha minus 1 times x alpha minus 1 min, in order to ensure that the integration from x min to infinity of C x to the minus alpha dx is equal to 1. Okay? Now, we have now this distribution, and now what can we say about it? Well, you know that, well, this is something that you've seen in the first year, that exponentials go very fast to 0 when x is large, much, much faster than any power of x. So it means now that, well, if you plot a distribution and that it is a power law, and as I said, we'll show why this is a straight line, but let's assume now that we know it's a straight line. How would an exponential or a Gaussian or any kind of exponential function look like in a log-log way? Well, you would get something that would probably behave like this and then go extremely fast to 0. So it means here that the kind of distribution you have would basically be, oh, excuse me, I have a tiny problem here. Yeah. So you would basically have a distribution that for the exponential goes very fast to 0, which basically means that actually the large values of the power law are much, much more frequent than you would have in an exponential or Gaussian distribution. So, and this is exactly what we mean by the tail of the distribution. You will have an over-representation of extreme events when you have such a power law distribution. But when you have a power law, you also have an over-representation of the small values. And typically, power law distributions are associated to a very large level of heterogeneity. You have a very broad spectrum of values with actually a huge, basically, variability, heterogeneity that would be present in your system. Much more than you would have for a Gaussian or an exponential, for instance. Now, what can we say about this distribution? Well, actually related to this over-representation of extreme events and to this very broad heterogeneity. Well, this translates into the behavior for the moments of the distribution. So if I calculate the moment of a power law distribution, what I would get is, so this is x min to infinity of x to the power beta p of x dx. This would be equal to alpha minus 1 divided by alpha minus 1 minus beta x min to the power beta, but only if beta is smaller than alpha minus 1 and it diverges otherwise. So it basically means that when you have a power law distribution, certain moments are ill-defined. And you will have that some moments are well-defined, but others will basically diverging, at least if you were to have like an infinite number of samples for your distribution. So it's quite important to observe that even something as simple as the mean would diverge for values of alpha that are between 1 and 2. And the variance itself would actually not exist for values of alpha that are between 2 and 3. So it means here that what you need to think is that if you have a power law with a value of 2.5, for instance, alpha equal to 2.5, it means that your average will be high, but your variance is infinitely large. And by what you understand, by what is the intuition of the variance tells us about what are the fluctuations around the average, yes? It basically means that you have infinitely large fluctuations, and actually that the average itself doesn't have any kind of meaning. Yeah? The average in a power law distribution such that the variance diverges, well, you can calculate it, but it's not representative of much. Now, just a tiny technical discussion. Well, clearly, if you were to calculate a certain moment, and you do it by measuring samples of your distributions, well, if so you calculate a certain moment x beta, and if your moment is converging, well, what you would expect is that you would have fluctuations, and then after some time, you're going to be converging to the value that is the actual value. Yeah. After taking sufficiently many samples, you converge towards the finite value, that is the expected value of your moment. But in situations when the moment diverges, of course, for any finite number of samples, you have a finite value. But what's happening instead is that you would get a value that basically fluctuates but continues to grow and to asymptotically diverge when the number of samples becomes sufficiently large. Now, something else that's quite important to keep in mind is that very often in real life situations, you never have a pure power law. So it means that, again, let's do it in a log way. Well, it means that very often you have distribution that may look like some sort of a straight line, but actually tend to show deviations, and typically deviations like those for small and for large values. Now, for the large values, this is something that can be understood relatively easily. When you have a finite system, you have finite resources. And so clearly, you will need to have a cutoff at some point for your distribution. And very often, these cutoffs take the form of some sort of an exponential cutoff that would basically be corresponding to the kind of shape we have here. So it means that even if power laws can be well-defined mathematically, typically in real life, but they tend to be observed only for certain regions of the values, and to show deviations clearly for the small and also for the large values. Now, actually, power laws have played a very important role in economics in order to describe the inequalities that may be present in populations. Let me just go back to. So you probably know that the world is clearly unequal, and you have certain people who are clearly more wealthy than others. Yes. And some question that has attracted a lot of attention, even more these years, is what is the level of inequalities that are happening in the population? And typically, what the people are interested in is to try to understand what is the fraction of the wealth that the richest people have. So if you take the 10% most wealthy people, what is the fraction of the wealth that they have? And of course, the larger is this value, the more unequal would be the society. While the smaller is this value, well, the more equal would be this society. Now, the thing is that when you're confronted to power laws, well, this question can be done relatively easily. So you can, for instance, calculate what is the fraction of people whose wealth is larger than whose wealth is larger than a certain value. Well, that would be equal to the integration from x0 to infinity of cx minus alpha dx, which is equal to x0 divided by x min to the power minus alpha plus 1. Yeah? So this is the fraction of people who have at least x0 in their bank account. But then you can also calculate how much money do these people have. And what it will give you is it's w of x0. And you can ask what is the fraction of the total money that they have. And so this is equal to the integration from x0 to infinity of x c x minus alpha dx divided by the integration from x min to infinity of x c x minus alpha dx. And if you do the math, you can see that this is exactly equal to the p of x0 to the power alpha minus 2 divided by alpha minus 1. So we have a relation between the fraction of the wealth with what is the fraction of the richest people that we consider. And we see that the whole dependency takes place as the ratio of alpha minus 2 by alpha minus 1. So clearly when alpha is very large, this whole thing disappears, right? And so we have that the total fraction of the wealth is proportional to the fraction of the population. It would be extremely equal. But when alpha becomes very small and goes to 2, actually we'll basically have instead that a tiny fraction of the population will possess a huge majority of the wealth. And typically the kind of curve that you expect is that when the alpha is very large, we have something like here, where that would be the wealth, that would be the fraction of the population. While if we have instead something with a small value of alpha, which means that we have a very flat Power distribution, and hence we have a distribution with a lot of heterogeneity, while basically we would have that small fractions of the populations possess a huge fraction of the wealth. Okay, so now what else should be said? Well, as I said, well, there are two important properties of power laws. So one very important property is that they tend to be scale invariant. So it means that they have this scale invariant property, and this is something that is very much important in situations where you have self-similarity. For instance, in statistical physics, that would be a property that is very critical to describe what's happening at transition, for instance. And what it means is that if you do P of C1x, this is the same C2 of P of x. So P of C1x means that I change the way I measure my position x. I change my units, for instance. So the distribution is, if I change my units, remains the same up to a constant. So if I change the way I measure things, if I zoom in, I zoom out, I take centimeters instead of meters, I will basically get the same distribution just up to a constant. Now, another very important property of Poirot distributions is the fact that they take the form of a straight line in a log-log plot. And how do we see that? We know that P of x is equal to C times x to the minus alpha. If I take the log of this, I have that the log of Px is equal to the log of C minus alpha times the log of x. And so we see here indeed that if I do a log-log, well, that would be my y-axis. This would be my x-axis. This is the equation for a line. And as is to be expected, the alpha that is appearing, well, when alpha is small, I have something that is very flat. When the alpha is large, I will have something that goes very, very fast to 0. And I will basically have that the tail of my distribution will not be that large anymore. So as I said, power law distributions are very, very important when you are dealing with real-life data sets, because very often you have a lot of heterogeneity that is present in data. And power laws are a simple way to model this kind of heterogeneity. And as we'll see, well, in networks specifically, a certain number of models are making the assumption that the underlying graph tends to have certain properties that are distributed in a power law way. But that would be for next week. So this was the last video for this week's course on networks, where we've been looking at certain mathematical concepts that we'll be needing next week and in the next weeks in order to model and to study the behavior of networks. I hope that you enjoyed it. And yeah, so please see you next week.